Hey everyone, congratulations on surviving Project 2. So today, I'm going to continue where I left off on Monday. On Monday, I was talking about ordered dictionaries. Ordered dictionaries being an abstract data type that allows you to do everything that a hash table can do, everything that a binary heap can do, and more. But I gave you an algorithm for implementing an ordered dictionary, which is called binary search trees. And binary search trees, unfortunately, are pretty slow. So we want to make them faster. Because having worst-case linear time performance per operation, you could do that with just a list. So we want something a little faster. And so today I'm going to teach a second data structure that also allows you to implement a ordered dictionary. This is called a 2-3-4 tree, and the interesting thing about 2-3-4 trees is that they're a tree that always stays balanced whenever you insert things into it, whenever you remove things from it. So again, a 2-3-4 tree happens to always be absolutely perfectly balanced in the sense that every leaf node is at the same level of the tree. And because it's perfectly balanced, all our favorite operations like find, insert, and remove take big O of log n time. In the worst case. So 2-3-4 trees are not binary trees. The name 2-3-4 is because every node has either 2 children, 3 children, or 4 children, unless it has no children at all and it's at the bottom level. So again, the exception is the leaves, the ones that have no children, they're all at the same level of the tree. And therefore, that's going to be the bottom level of the tree because there's nothing underneath it. Each node also stores a variable number of keys. It's not one node per key anymore. You could have 1, 2, or 3 entries in each node of the tree. And there's a relationship that never changes, which is the number of children that a node can have, if it has any children at all, is the number of entries plus 1, unless, again, it's a leaf node at the bottom of the tree, in which case it has 0 children. So all of this will probably make more sense when I draw a tree. So here's what a typical 2-3-4 tree looks like. I'm starting with the root node at the top, and this particular tree happens to have 3 entries in the root node with keys 20, 40, and 50. So since it has 3 keys, if it has children, it has to have 4 children. And so let's suppose those are the children. And in this tree, they're going to have children too. Now, when you look at this tree, you can probably see that the keys are in a particular order. So just like binary search trees have a binary search tree property, where all the keys less than the root are on the left side and all the keys greater than the root are on the right side, here we've got a tree that's divided into parts according to the keys in the root. So you have this subtree here, which is all keys less than or equal to 20. You have this subtree here, which is all keys that are between 20 and 40. You have the third subtree here, which is all keys that are between 40 and 50. And the last subtree is all keys that are greater than or equal to 50. So the three keys in the root node subdivide the children appropriately, partition the children into different groups. And that happens recursively. So the 14 key here has keys less than 14 in its left subtree and keys greater than 14 in its right subtree. And here we have a 2-key node, 70 and 79, so its children get divided into 3 groups: keys that are less than 70, between 70 and 79, greater than or equal to 79. Another thing you'll notice about this is that you could do an in-order traversal on this just like you would do an in-order traversal on a binary search tree, and you would list all the numbers in sorted order. So if you do an in-order traversal on this tree, you start by visiting the 10, then the 14, then the 18, then the 20 at the top, 25, 32, 33, 40, and so on. So you can write a recursive in-order traversal of this tree that gives you all the numbers in sorted order. So one thing I want to warn you about before I start talking about details of operations on these trees is that the 2, 3, 4 tree operations I'm going to teach today are not the same as in the Goodrich and Tomassia textbook. There is a difference because there's more than one kind of 2, 3, 4 tree. And the difference isn't the data structure. The difference is in the algorithms by which you insert and remove keys or entries in a 2, 3, 4 tree. Goodrich and Tomassia use what are called bottom-up 2, 3, 4 trees. And these have the advantage of being easier to understand, but they're not the fastest version. What I'm going to teach you today is something called top-down 2, 3, 4 trees. The difference between the two, both kinds of trees, you start at the root, you walk down looking for something. In bottom-up 2, 3, 4 trees, you sometimes have to restructure the tree after you do your search, in which case you start going back up the tree as necessary to restructure and rebalance the tree. With the top-down 2, 3, 4 trees, we don't have to go down the tree and go back up again. We just go down the tree once, but we are restructuring the tree as we go down right from the start. We don't wait until we find what we're looking for before we start changing the tree to improve its balance. And so we're learning these because they're faster. I also want to mention that 2, 3, 4 trees are a special case of what's called a B tree. B trees are extremely important in database systems. It's very common when you have a database on a disk that disk sectors are arranged to be nodes of a B tree. You'll learn about that if you take a database course, but this will give you a head start on understanding the algorithms that are used in databases to store large amounts of information on disks. Okay, are there any questions about the structure of a 2, 3, 4 tree? So, let me talk first about searching in a 2, 3, 4 tree. So the search operation is probably going to be pretty obvious to you. We are using exactly the same prototype here as we did for binary search trees. And the algorithm for finding something in a 2, 3, 4 tree is essentially the same as it is for a binary search tree. Obviously, you have to adjust it a little bit to take into account the fact that nodes can contain more than one key, but the adjustment is pretty obvious. So like, suppose that I want to do find 74 on this tree. Well, what do? I look at the top node and I ask myself, is 74 less than 20? Is it between 20 and 40? Is it between 40 and 50? Is it greater than 50? It's greater than 50. So, I start at the root node. I follow this arrow down to this child because 74 is greater than 50. I now visit this node, and once again I compare 74 with the keys in that node. 74 is between those two keys. It's between 70 and 79. So I'm going to take the middle branch down to this child here, and sure enough, there I find the 74 that I'm looking for. That's find. Any questions about the find operation? Things get more challenging with the other two operations, insert and delete, because when you insert something or you delete something, you have to restructure the tree to make sure it stays balanced. So we're going to see how you do that. So the second operation we're looking at, once again, the insert method on a 2, 3, 4 tree has exactly the same prototype as it has with a binary search tree. Because we're doing the same thing on the surface, it's still an ordered dictionary. We want to insert an entry whose key is k and has some associated value v, or e in this case. Why is that e? Yeah, v. All right, so insert, of course, walks down the tree in the same way that find does. You walk down the path as if you were doing a find, and of course the reason find works is because it follows the same path that insert follows. One difference between insert and find, of course, is that if you're going to find k, and k is already in the tree, you stop as soon as you find it. If you're going to insert k, and there's already a k in the tree, it's okay to have 2 or more copies of the same key. So as you're searching for k, if you actually find k, well, you want to insert another k. So you just go to the left of the existing k and keep searching down the tree until you reach a leaf. you have to reach a leaf to insert a new node. Now, one big difference between find and insert, and this is a really crucial difference, is as we walk down the tree, we're going to occasionally restructure it. We want to restructure it in such a way that when we get to the bottom of the tree, there will be room for the new key to be inserted. So the way we restructure it is whenever we encounter a node that has 3 keys in it, we're going to take the middle of those 3 keys and move it up into its parent. Now, the reason why we can always take the middle key and move it up to the parent is because the parent has at most 2 keys. Why does the parent have at most 2 keys? Because we treated the parent the same way when we visited it. So the parent will have at most 2 keys. Because we treated it the same way, so it always has room for a third. So when you do this, it's a little more complicated than just moving a key from a node to its parent. You wind up restructuring the children of the parent as well. And here's how that works. Suppose that this is a part of a 2, 3, 4 tree, or maybe this is the whole 2, 3, 4 tree. So maybe I want to insert 13 or something, and so I'm walking down this tree and I reach this 3-key node. Whenever insert is walking down the tree and hits a 3-key node, it always takes the middle key and moves it up into the parent. And so that 11 is going to move up beside the 20. But I also have to restructure this child. Why? Well, the parent has 2 keys now, 11 and 20, so it's got to have 3 children. And those 3 children have to obey the 2, 3, 4 tree invariant. And so that means the 10 has to go here, the 12 has to go here. Now 10 and 12 are in separate nodes. They're not in the same node anymore. When we moved the 11 up, we split the 10 and the 12 up into 2 separate nodes. And the 30 is still here where it was before. So that's our basic restructuring operation. As we walk down the tree, every time we hit a 3-key node, we're going to do that basic restructuring operation. So let me demonstrate how that's going to work out on the tree that we started with. So let's take this tree again, and now we're going to look at the operation insert 60. So what happens when we insert 60? We have to start at the root of the tree and walk down the tree trying to find 60. And the root node already is a 3-key node. Whenever we hit a 3-key node, we're going to restructure it by moving the middle key up into the parent. This is a special case, though, because the root node doesn't have a parent. So we'll create one. So the first thing we do here is we restructure this node by moving the 40 up into a separate node on its own. The 20 and the 50 become separate 1-key nodes, instead of being all together in a 3-key node. And so the stuff in the middle goes away. So we've just created a new root node with a 40 in it. It now has 2 children, 20 and 50. The 20 still has 2 of the original 4 children of the original root node. The 50 has the other 2 children. And from there we can continue moving down the tree, searching for 60. So 60 is bigger than 40, so we're going to search to the... Why is this in such a bad mood today? We're going to search down to the left. From the 50, we're going to search down to the right. So from the 40, we search to the 50. From the 50, we search to there, 2-key node. And then finally, since 60 is less than 70, we search down to this 3-key node right here. And so this being a 3-key node, we have to do the same rule that we did before, which means we're going to take that 62 and we're going to move it up into the parent there. And so after we do that, it's going to look like this. We've got a 62, a 70, a 79, all in that node up there. The '57 is now alone in a node by itself. And so all of this gets replaced by this. So again, these 2 were in a 3-key node. Now they're in 2 separate nodes by themselves. The 62 moved up. Now this is a 3-key node, but we're not going to go back up and restructure that again. Maybe we'll restructure this next time we come down the tree. But when you kick a key upstairs and that creates a 3-key node, you don't restructure that 3-key node, not until next time you traverse down that branch. Finally, now that we have restructured the tree, the place that we land when we're searching for 60 right here only has 1 key now. And so there's room for another key, and so we can add the 60 there. And so we wind up with a 2-key node where we've just inserted the new key 60. Now, why did we do all this work? Why did we restructure the keys as we went down? Well, you'll notice that the original node where we would have put the 60 already had 3 keys in it. So there wasn't room to put the 60 there. The point of the insert operation is to make sure that there will be room in every node to put the key when we get there, and therefore we restructure 3-key nodes by pushing keys up the tree. Any questions about that, how insert works? Yeah. So if we had tacked on a new child to 57 instead, like if we'd put the 60 here as a child of 57, then the tree would not be balanced anymore. And the whole purpose of this data structure is to make sure that the tree always stays balanced. When you just look at one insertion, it doesn't seem to make much difference. But if you inserted lots and lots and lots of keys all in the same part of the tree so that one part of the tree got really deep, then you would begin to see that it's really important to restructure as you go so that once enough keys get inserted, you don't get more and more imbalance, as would happen if this kept going down. Other questions? Yeah. So in every node, you can store two things. There's the key that you're using to search, but there's also associated data that goes with that key, which could be almost anything. So in the dictionary example I gave it like a few weeks ago, the keys were words and the associated values were dictionary definitions. Another very common thing is in a phone book, the keys would be the name that you want to look up alphabetically, and the associated value would be the phone number. Other questions about that? All right, definitely the hardest part of a 2-3-4 tree is the remove operation. How do you remove keys? So, for obvious reasons, remove starts the same way that find does. You find the key that you're trying to remove, okay? And in some ways, it's just like a binary search tree. So, if the key is in a leaf, you can just remove it from the leaf. If the key is in an internal node, we're going to do the same trick that we did for binary search trees. Basically, you replace it with the next higher key, or the next key in the in-order traversal after the one you're removing. So a 2-3-4 tree is just like a binary search tree in that you cannot remove an internal node from the tree, but what you can do if you want to remove a key that's in an internal node is go find a key in a leaf node that you can remove and then move that key up to replace the key in the internal node. So we're going to do that exact trick, but remove, just like insert, as it's walking down the tree, restructures the tree. Insert restructured the tree to make sure that when you reach the bottom, there will always be room in that leaf to insert a new key. Remove is going to do the opposite of that. It's going to restructure the tree to make sure that when you reach the bottom, you'll wind up in a leaf that has at least 2 keys, so you can always remove one without leaving the node empty. That way the tree stays balanced. So remove changes the nodes as it walks down, kind of like insert does, only it's more complicated because now we are eliminating not 3 key nodes, we are eliminating 1 key nodes. With the exception of the root. If the root has 1 key, there's nothing we can do about that. And the reason we eliminate one key node is so that when we get to a leaf at the bottom, it will have at least 2 keys. We can delete one of those keys without leaving the leaf node empty, because you cannot have empty nodes in a 2, 3, 4 tree. If you do, then the balance still is screwed up. So a difference between insert and remove is that with insert, when we want to restructure a 3-key node, we always do it essentially the same way. There's just one way to do that. With 1-key nodes, when you're trying to eliminate a 1-key node, unfortunately there is not one method to do that that always works. So I'm going to give you 3 methods for removing a 1-key node, and always at least one of them can be applied. So the first one we try is something called a rotation. We always try rotations first. So let's suppose that remove encounters a 1-key node, and it's not the root. Then we try to steal a key from an adjacent sibling. So here's what that looks like. Here's part of a 2, 3, 4 tree. So suppose I'm walking down this 2, 3, 4 tree. Maybe I'm wanting to remove 29 or something. And so I wind up visiting this 30 node here in the middle. So when I visit 30, that's a 1-key node. I don't like 1-key nodes. I want to do something to get an extra key into that node. So what do? Well, I look at the sibling, and the sibling has more than 1 key here. So let's steal one. So what I'd like to do is I'd like to take the 50. Ideally, I'd like to take the 50 and move it over here next to the 30, but that's not going to work because of the search tree invariant. 50 is not less than 40, so I can't just go and take 50 and put it here. To fix that problem, I'm going to do something just a little more complicated. I'm going to take the 50, move it up to the parent to replace the 40, then I'm going to move the 40 down here next to the 30. And so that looks like this. The 50 moved up. The 40 came down next to the 30. And the rightmost node still has the 51 and 52. So we're still in that middle node, and now from that middle node, we can continue to search down the tree. Or if this were a leaf node, we could stop here and maybe delete something if there's thing that we're looking for is there. The reason this is called a rotation is because, remember, the 50 moves up and the 40 moves down. So if you think of both motions together, it kind of looks like you're rotating several keys. There is one other bit of restructuring going on here besides moving the keys. You'll notice that when we started, this node has 2 children and this node has 4 children. But when we're finished, this node has 3 children and this node has 3 children. So some children had to get moved around a bit. In particular, there was a subtree here hanging off the left side of the 50, which is now hanging off the right side of the 40. Now, that subtree, by the search tree invariant, is full of keys that are between 40 and 50. And here it's still full of keys that are between 40 and 50. So we're still good. But you do have to reorganize the children of these nodes for the restructuring to work correctly. By the way, Goodrich and Tomassia call these transfer operations for some reason, but I prefer the name rotation. And one thing I want to point out is that you cannot steal a key from a sibling that is not adjacent. So if you come visit the 10 instead of visiting the 30, you're out of luck because you can't steal a key from its adjacent sibling. The adjacent sibling only has one key. It has nothing to steal. And this one is too far away. You can't steal a key from here to get into there. Yes. Sorry, what only had 2 entries? Uh-huh. Yes, you can steal a key from a 2-key node. And it's true that that only leaves that node with 1 key, but we're selfish. We don't care if the next door neighbor has only 1 node as long as we have 2. So sometimes you cannot do this operation because none of your immediate siblings have more than 1 key. And in that case, we go on to try a second thing. If no adjacent sibling has a key, what do we do? Well, then we do sort of the opposite of what insert does. We steal a key from the parent. And because we previously treated the parent the same way, the parent will have at least 2 keys, so it's always got one we can steal. Unless it's the root. The root's special. Question? Uh-huh. Say that louder, please. Yes, you can steal a key from your left sibling or your right sibling. As long as it's an adjacent sibling, left or right will do. Mm-hmm. Yes? We were removing something in 30's subtree, which may or may not be 30. Doesn't really matter what, it could be 30. Uh-huh. Uh-huh. To 30's subtree. Oh, it's left subtree. So I'm not sure I understand what you're asking, but before 30, this left subtree here, which is now here. Oh, I see what you mean. Yeah, so when you are removing something that's not in a leaf node, then you can't remove the 30 directly. What you have to do is you have to remove the next largest key, which is in a leaf node, and then you move that key up to replace the 30. And then I'll show you an example of that later. So coming back to part 2, here's what we do when your siblings only have 1 key. So in this example, all three of these children only have one key, and let's suppose I'm visiting the leftmost one. Let's suppose I'm visiting the 10 right now. So I can't steal the 30 because I can't leave a node empty. But the parent has 2 keys, so I can steal the 20. And that means the 20 comes down, leaving just the 40 in the parent. When the 20 comes down, since all you have left is 1 key, there can only be 2 children. There can't be 3 children anymore. So how does that work out? Well, what we do is we put the 10, the 20, and the 30 all together into one big node. Meanwhile, the 50 is untouched. So you wind up taking 2 children nodes and fusing them together with the addition of one of the keys from the parent. And therefore, that is called a fusion operation. And of course, where the 10 had 2 children, 2 subtrees, the 30 had 2 children, now all 4 of those children are children of this one node here. Any questions about the fusion operation? All right, there's one more special case, which is really a special case of the fusion operation, which is, it's like the fusion, except the parent is the root and only has 1 key. So the root is the one node where we cannot make sure that it has more than 1 key. So if the parent is the root and has 1 key, then that's a special case. And also if the siblings, the adjacent siblings, only have 1 key, well, there's 1 sibling now. Then what you do is you still do a fusion operation, but now you're actually pulling down the root node and combining it with its 2 children. So all 3 nodes together become 1 node. And when you fuse the root and both of its 2 1-key children together, that node becomes the new root. To give you an example of these 3 rules working together, let's go back to the tree that we restructured earlier. This one here. And let's ask ourselves, what happens to this tree if I do remove 40? All right, I want to remove 40 from this tree. I start at the root, and lo and behold, I have already found the 40. So, what do? Well, I can't just take the 40 out of the root node and leave it there. I have to replace it with something else. I need to fill that space. So what we're going to do is we're going to look for the next larger key, or the next key in the in-order traversal after that 40, which is that 42. And that 42, once we find it, we'll have to move up to replace the 40. But we haven't found the 42 yet. We don't even know that there's a 42 down there. At this point, we're still in the root node. And so all we can do is erase the 40. And I'm going to just leave a bookmark here. I'll write XX to remind me that when we get to the bottom of the tree and find the 42, I want to move it up into that location. The second thing I do is I start walking down the tree looking for the next key in order after 40. Or in other words, I go to 40's right subtree and then go to the far left and find the minimum item in that subtree. So that means next I walk down to this 50 node here. And that's a one-key node. We don't like one-key nodes. When remove finds a one-key node, we get rid of it by, well, first we look at the sibling. Does the sibling have a key I can steal? No, the sibling only has one key, the 20. I look up to the parent. Does the parent have more than one key so I can steal one of its keys? No, it doesn't. But the parent is the root, so this means that we're now in case 3, the last case I told you about, where you take the root and its two children and you conglomerate those all into one 3-key node. So that means remove the barriers between these two nodes and turn this back into a one-key node with 20, a placeholder in the middle, and 50 as my keys. All right, now I can continue searching down the tree. So I continue now to the node that contains the 43. And at this point, does the 43 have a sibling that I can steal a key from? Well, actually it does. This is its sibling here. At this point, things are getting complicated, so let me redraw the tree. So we've just come down to the 43, and we want to steal a key from its sibling. So we're going to steal that 62. So here's what those two nodes look like at this point. I want to steal the 62 and move it to its sibling, but the 62 can't go straight to the sibling. If we do a rotation, the 62 goes up to replace the 50, and the 50 comes down next to the 43. So now that's what the tree looks like after I steal a key by rotation to change this one key node into a 2-key node. Now that I've done that, I can continue moving down the tree. Remember, I'm looking for the smallest key in that subtree. So I walk down now to the 42. The 42 is a 1-key node. Can I steal a key from its siblings? No, I can't. 47 only has one key. So I'm going to steal now a key from its parent. I'm going to take this 43 here, and I'm going to move it down and combine it with the 42 and the 47 so that they all become one node. All right, so I finally reached a leaf node, and because of my restructuring the tree, that leaf node has more than one key now, and I can safely remove a key without leaving that node empty. The key I want to remove is this 42, so this can go now. And remember, the reason we wanted the 42 is because we have this placeholder up here in the root node, which I now want to replace with the 42. And that completes that remove operation, which was deliberately chosen to be as complicated as possible. Any questions about remove? Yeah. Mm-hmm. Okay, the question is, when we're trying to get rid of one key nodes, why don't we do that only at the leaf node? The answer is, suppose you get to the leaf node, and it's a one key node, and its sibling is a one key node, and you look up at the parent, and the parent is also a one key node. Then there's nowhere to steal a key from, and you're shut down. So we want to make sure that when we get to a leaf, the parent has at least two keys as well. And that means we want to make sure that when we get to the parent, that its parent has at least two keys as well, just in case we have to steal a key for the parent. And so on all the way up. Other questions? All right, so the bottom line is running time. So let's think about what is the height. Sorry, if you know the height of a 2, 3, 4 tree, if it has height h, how many nodes can it have? Well, it has at least 2 to the h nodes. Sorry, it has at least 2 to the h leaves, pardon me. And it has at most 4 to the h leaves. It would have 4 to the h leaves if every node has 4 children, except at the bottom level. So, the total number of entries, call it n, is always greater than or equal to 2 to the power of h plus 1 minus 1. That would be in the case where every node has only 2 children, except at the bottom level, then you would have at least this many entries. And your TA should discuss in discussion section where that expression comes from. And so, once you know that, then you can take the logarithm of both sides, and that gives you that h is in big O of log n. So, the height of the tree, the height of a 2, 3, 4 tree is never bigger than the log of the number of entries in that tree. And so that means we get log n performance on all the operations. The other reason why we know that is because the time spent visiting one node is in big O of 1. It might be a big O of 1 because these fusion operations and these rotation operations are kind of expensive, but even so, each of those operations only takes a constant amount of time at each level of the tree. And so that's why find, insert, and remove all have worst case times in big O log n. It's because, well, the running time is big O of the height of the tree. The height of the tree tells you how much work you'll have to do to insert or remove or find something. And we know that's no bigger than log of n. And just for comparison, remember that binary search trees, although they can be fast, they often are fast, they can be really slow in the worst case. So 2, 3, 4 trees are a big improvement. Any questions about that? Yeah. How do you create a 2, 3, 4 tree? Like, what does an empty one look like? So an array isn't really a natural way to store a 2, 3, 4 tree. There's some data structures like binary heaps that just naturally fit into arrays, and there are some data structures like 2, 3, 4 trees that really don't. So the way you would do a 2, 3, 4 tree is you would create a tree node object, kind of like a list node object, that has a parent pointer and 4 child pointers. And yes, if you have a list of elements and you want to put them into a 2, 3, 4 tree, you just insert them one by one. I don't know of a more efficient way. Yeah, it is n log n to create a 2, 3, 4 tree in general. I do know a way to do it faster, but it's going to require a lot more technology that we'll learn later this semester. Yes? You have one root node, it has 3 children or 3 keys? Okay, one node, 2 children. 2 children with 3 keys each. Okay. Oh, no, the root is special. If the root has 1 key, there's just nothing we can do about that. So we just leave the root as 1 key. I'm going to change the topic altogether now. So that's it for 2, 3, 4 trees. Now I'm going to talk about graphs, and this discussion will continue into the next lecture. I hope most of you have seen graphs before in some context. Maybe if you've taken CS70, you've definitely seen lots of graphs. But you've probably seen them before that. So a graph is a set of vertices and edges that connect those vertices together, and I'm sure you know what they look like. In fact, they look a lot like trees, except that there can be more than one path between any 2 nodes. And we have a notation that mathematicians like to use for graphs, which is we write G equals, open parenthesis, V comma E, close parenthesis. And this VE is what's called an ordered pair, which sounds a lot deeper than it actually is. Mathematicians just love extraneous rigor sometimes, but this notation just happens to be convenient when you have 2 different graphs that have, for instance, the same vertices. So you could talk about the spanning tree of a graph being some other ordered pair VF, and you notice that the vertices of the 2 graphs are the same. That's where that can be useful. Graphs come in 2 types. There are directed graphs. There are undirected graphs. And in a directed graph, or what's sometimes called a digraph for short, every edge is directed from one vertex to another vertex. So let's say it's directed from some vertex, call it V, to some other vertex, W. Or maybe to the same vertex. You can have an edge directed from a vertex to itself. So we will draw that like this. Here's a vertex V, here's a vertex W. The edge will have an arrowhead that tells us which way that edge points. And we will often write, if this edge we call it E, we can write that also as an ordered pair. So if we write E equals VW, that's our way of saying that E is an edge that points from V to W, and V is called the origin of the edge. And W is called the destination of the edge. Whatever is being pointed at is the destination. Now, in an undirected graph, well, we still have pairs of vertices that are connected by edges, but now we don't draw an arrowhead. Now that edge just connects the two vertices in no particular order. And so we're still going to write E equals VW, but now it's an unordered pair instead of an ordered pair. What does that mean? Unordered pair is a mathematical way of saying that VW and WV are considered to be the same thing, the same mathematical object. In a directed graph, they're not the same thing. In a directed graph, there's a world of difference between V and W versus WV. It's like driving down the wrong way down a one-way street. But an undirected graph, the edge is like a two-way street. And so, as you might suspect, a very common purpose of graphs is to model street maps. So here's an example of a graph that you might find somewhat recognizable. I'm going to use the nodes of this graph to represent intersections. And I'm going to use edges as a way to represent ways to get from one intersection to the next intersection. But since this is a map of one-way streets, I'm going to use a directed graph and directed edges. And this is a graph that most of you have personal experience with. So, streets south of campus. Because there are one-way streets, it's just natural to use a directed graph for that. There are other examples of things where it's really natural to use an undirected graph. Like, let's suppose you want to know what cities in the East Bay are adjacent to each other, like share a border, and which ones don't. Well, if Albany shares a border with Kensington, then obviously Kensington shares a border with Albany, so it doesn't really make sense to use a directed graph here. So there's some of the East Bay cities around us. And I'm going to use these graphs for a few examples shortly, so it's worth keeping copies of them around. So the set E in a graph is a set of edges. And in a set, you can't have two copies of the same thing. So in a graph, we don't have the concept of there being two copies of the same edge. Having said that, a digraph, a directed graph, may contain both an edge VW and an edge WV, because they're not the same edge. They're two completely different edges. They're not considered identical in a directed graph. Both kinds of graphs, we're going to allow self-edges. And a self-edge is an edge of the form VV. It connects V to itself. A lot of applications don't use self-edges. Neither of these two graphs I've drawn here, neither of them do self-edges really have any meaning. But there are graphs where self-edges do have some sort of meaning. We're going to need some definitions that we're going to use later for a variety of reasons. So here's a few definitions about graphs. There are paths through graphs, just like there are paths through trees. A path is a sequence of vertices. And we require that each adjacent pair of vertices in the sequence is connected by an edge. And if the graph is directed, there's an additional requirement, which is that the direction of the path has to be aligned with the edges. You cannot go the wrong way down a one-way street. When we have paths, we will often talk about the length of a path. And the length of a path is defined to be the number of edges that the path traverses. And so, for instance, in that Berkeley intersection map I showed you, south of campus, here is a path, 4, 5, 6, 3. It's a perfectly good path, follows the edges, goes the right way down the one-way streets, and it has length 3. Because we're counting edges, not intersections. And a path, if you're going in circles, you can take the same edge more than once. You count every time you traverse the edge, not just once. Also, it's perfectly respectable to talk about a path of length 0. So let's suppose I have a path that just has one node. We start and we end at intersection 2, and we don't actually go anywhere. Well, that is a path. It's just a very short one, a path of length 0. And sometimes we'll talk about the distance from one vertex to another, which is the length of the shortest path that connects them. Question? Self-edge what? So it depends whether you use it. So if I have a path 2, 2, that's a path that starts at 2, follows a self-edge once, and winds up back at 2. Then that's a path with length 1. But for that matter, I could use the self-edge more than once. If there's a self-edge connecting 2 to 2, I can follow the path 2, 2, 2, and that actually has length 2. So you count every edge you follow, and you count it every time you follow it. Sometimes we'll talk about a graph being strongly connected. A graph is strongly connected if there's a way to get from every vertex to every other vertex. So for example, a street map will almost always be strongly connected. Even if there's one-way streets, there's almost always a way to get from any one point on the map to any other point on the map. And if you can't, then you're stranded for life in some region, which would be very strange. When we talk about the word strongly connected, usually that phrase is usually used just for directed graphs. When it's an undirected graph, we just say it's connected. You can say strongly connected, there's nothing wrong with that, but in undirected graphs, theorists usually just say connected instead of strongly connected. But at any rate, both of the graphs I showed you are strongly connected. We will often care about the degree of a vertex. And that is the number of edges incident on the vertex. By the way, self-edges count just once. Or at least they count just once in 61B. I'm told there's some math course that some of you take where they prove some theorem that requires self-edges to count twice, but we're not doing that here. So, like, going back to the map we had here, Berkeley has degree 4, because it's connected to 4 other cities in this graph. And Piedmont has degree 1. Usually if we use the word degree, we're probably talking about an undirected graph, because when we're talking about a directed graph, we usually use the words in degree and out degree instead. So in a directed graph, the in degree is the number of edges that point at a vertex. And the out degree is the number of edges pointed away. So once again, going back to the street map example, if you look at intersection 6, it has in degree 2 one-way streets going to that intersection, and out degree 1. I could draw a better one. There we go. So I want to talk first about how to represent graphs, and then about algorithms, some simple algorithms we can do on graphs. Are there any questions about any of these definitions? All right, let's question over here. Can a what? Oh, yeah. Can a directed graph be connected but not strongly connected? There you go. That is a directed graph that is connected but not strongly connected. So there's no way to get from vertex W to vertex V, so it's not strongly connected. The most obvious way to represent a graph is with what's called an adjacency matrix. And that is a V by V array of Booleans. By the way, I don't know if I've mentioned this before, but this notation here where you take a set and you put it in absolute value signs, that is called the cardinality of a set, which just means the number of things in that set. In this case, putting the little vertical bars around V means the number of vertices. So we take an array, a two-dimensional array of Booleans, that has one row for every vertex and one column for every vertex. And so let's look at our intersection graph, for instance. Here are the indices for my 2x2 array. To keep this short, I'm not going to write true or false in every box. I'm just going to write a T wherever an entry is true. And a little dash wherever they're false. So that's what an adjacency matrix looks like for the street intersection map graph that I drew before. And we are interpreting it as going from the origin numbers here to the destination numbers here. So in other words, if you look at this true here, that means that we have an arrow that goes from vertex 6 to vertex 3. We do the same thing for the city map. I won't draw the whole thing, I'll just do the first 4 cities. And so that looks something like this. Now, since this is an undirected graph, you'll recall, the city adjacencies are an undirected graph, this matrix, this adjacency matrix, is symmetric around the diagonal. So Berkeley's connected to Albany, Albany has to be connected to Berkeley. So it's pretty easy to see that the maximum possible number of edges you could possibly have in a directed graph is v squared. For an undirected graph, it's a little bit more than half of that. It's not v squared because the Berkeley-Albany edge is the same as the Albany-Berkeley edge. In an undirected graph, they're not considered to be two different edges. So you roughly divide the number in half, except you don't divide the south edges in half. So you get just a little bit more than v squared over 2 possible edges in an undirected graph. But there are many, many graphs that you will use in applications that don't have that many edges. One example is planar graphs. A planar graph is any graph that can be drawn in the plane without edges crossing. And it is possible to prove with some work that if you have a graph in the plane, no edges cross, it can't have v squared edges. It can't even have more than a linear number of edges. They have at most big O of v edges. So planar graphs are pretty compact. If you're using an adjacency matrix to store a planar graph, you're kind of wasting a lot of space if it's a big graph. So we say that a graph is called sparse if it has far fewer nodes than the maximum possible value. Sorry, if it has far fewer edges than the maximum possible value. And you'll notice that this is kind of a fuzzy definition. The word sparse does not have a rigorous mathematical definition. It's more of a loose term. One person's sparse might be another person's dense. But if you have a subquadratic number of entries, usually you would consider that sparse. So for things like a sparse graph, you want to be able to take advantage of the memory savings you should get by the fact that you're not using most of the edges. And so we have something called an adjacency list, which is an alternative to adjacency matrices for representing graphs. So those are the two main ways we're going to represent graphs in this class: adjacency matrices, adjacency lists. An adjacency list, it's a bit of a misnomer because it's not one list. An adjacency list is actually a collection of lists. And so each vertex v in the graph is going to have its own list of edges directed out from v. And when I say list, you can use any list representation you want. Array lists, linked lists, even binary search trees. So here's one example of how you can do this. For our intersection graph, I'm going to use an array of arrays. So what that means is at the top level, I have an array that has one entry for each of the 6 intersections. And that array is going to be an array of lists. And I'll use arrays to store my lists. So when you're leaving intersection 1, you can go to intersection 4. That's a list, but it's only got one item in it. When you're leaving intersection 2, you can go to intersection 1. When you're leaving intersection 3, you can go to intersections 2 and 6. So that's an array of length 2. When you're leaving intersection 4, you can go to intersection 5. When you're leaving intersection 5, you can go to intersections 2 and 6. From 6, you can get to 3, and that's it. So this is the simplest kind of adjacency list, an array of arrays. For the city graph, things are a little bit more complicated. One reason is it made it really easy that the intersections were numbered in order from 1 to 6, so I can just use an array. If I have city names instead of integers that are in consecutive order, then maybe I need to do something more complicated like a hash table. So I could have a hash table that maps from Albany, the string Albany, to a list, which is a linked list of cities that are adjacent to Albany. So Albany is adjacent to Kensington and Berkeley, so here I'm using a linked list for that, just for variety, and to remind you that you can use any list representation you want. And Kensington has a linked list of neighbors, which include Albany and Berkeley. And so on. I won't do the whole adjacency list. Regardless of the details of the data structure, whether you use linked lists or arrays, whether you use a hash table to map from your item names to your linked lists or not, the total memory used is linear in the number of vertices plus the number of edges. And I hope it's clear why that's true. So if the number of edges is a lot less than v squared, then this is a lot less than v squared. You've saved a lot of memory by using an adjacency list instead of using an adjacency matrix. Are there any questions about this? All right, I'm going to write down something I just said, which is, if your vertices are consecutive integers, then you're in luck. It's easy. You can just use an array of lists. And that allows you to find any vertex's list, obviously in constant time. But if the vertices are not expressed as integers, if they are arbitrary labels like the string Albany, then you can use a hash table to find your list. And so when you use the hash table, the key is the vertex object, and the associated value stored in the hash table is the actual list in which you store its neighbors in the graph. And let me remind you that an adjacency list is more space efficient and usually more time efficient when you are working with a sparse graph. But suppose you have a graph that has every possible edge. A graph that has every possible edge it could have is called a complete graph. Every vertex is connected to every other vertex. And when you have a complete graph, an adjacency list is less efficient. It's not asymptotically less efficient, but it's maybe takes a factor of 2 or 3 times as much memory as an adjacency matrix would. Any questions about that? Yes? Well, arrays are just much more efficient way to store things than a linked list. A linked list, you have object overhead for every list node. A linked list, you have a next pointer for everything that you're storing. So a linked list takes a lot of space. An array takes substantially less space if it's just a straight up array of simple primitive values. And in this case, we're using Booleans. If you have an array of Booleans, you can actually put 64 Booleans in one 64-bit word, and then you really get space efficiency like you could never have with a adjacency list. Question back there. An adjacency list, it's not faster to look up an edge. Sorry, an adjacency matrix, if you want to know if a particular edge is there, you can look that up in constant time because you just look at the coordinates in the array. If you want to know not whether a particular edge is there, but rather what is the first edge out of this vertex, an adjacency list might be faster than an adjacency matrix, because you don't have to search through the whole row to find an edge. So it's not a simple trade-off. You can't say one is always faster than the other. It depends what you're doing. So let's see an algorithm. We've seen tree traversals. We also care about graph traversals, which are more complicated than tree traversals. But just like a tree traversal, a graph traversal is a way of visiting every node in a graph once. And a lot of you already have experience with this because you had to go and learn depth-first search in advance to do the network identifier in your project. But for those of you who haven't already studied that, let's take a look at basic graph traversals. And again, a graph traversal is a way of visiting each vertex once. And there are two really famous graph traversals called depth-first search and breadth-first search. Depth-first search, which we often initialize to DFS because depth-first search is a long, unwieldy name, sort of searches a graph as deeply as possible, as early as possible. I'm not speaking rigorously here, I'm speaking colloquially. But one way to think about it is if your graph happens to be a tree, because every tree is a graph, some graphs are trees, then DFS performs a pre-order search on that tree. But depth-first search is more versatile than a pre-order traversal because it works on things that are not trees. And for contrast, we'll also learn breadth-first search on Monday. Again, long unwieldy names, we usually just call it BFS. What breadth-first search does is it moves outward sort of continuously and smoothly in all directions from the starting node. So it visits, first it visits the vertex that you choose to start the breadth-first search at. Then it visits all vertices whose distance from the starting vertex is 1. And then it visits all the vertices whose distance from the starting vertex is 2, and then 3, and so on. So if your graph is a tree, then breadth-first search is actually doing a level order traversal on that tree. So the most important difference between a graph and a tree is that in a tree there's only one way to get to a particular node. In a graph you might find yourself visiting the same node multiple times, coming at it from different directions. So to deal with that, we want to make sure that we only ever visit each node in a graph once, but we can approach it multiple times from different directions. So we need to be able to recognize that we've already visited this node and we don't want to visit it again. So for each vertex in the graph, we are going to have a Boolean, or what we call a flag, called the visited flag, that tells us whether or not this vertex has already been visited or not. And if it has been, we don't visit it again. So that way we never have to visit a vertex twice. We just remember which ones we've already visited. I am going to give you a depth-first search algorithm that's recursive, and if this is actually going to visit every vertex once, the graph has to be strongly connected, or maybe it won't visit every vertex once. So just assume for now that the graph is strongly connected. How DFS works is when DFS visits a vertex, call it U, it checks every edge going out of U. In other words, it checks every edge in the graph of the form UV. And then it checks whether V has been visited yet or not. If V has not been visited, we go visit it recursively. All right, I'm going to scroll this up here so I can give you code now. I'm going to put code inside a class that I'll call graph. And so we will have a public method called DFS for depth first search. And you pass in a starting vertex U. Now, I'm going to assume that before we call this, that we have some other piece of code that goes through all the visited flags and sets them all to false. We have to do that for this code to work. This code only works if we've already set all the visited flags to false. So DFS is going to be recursive. We start at one node and then we recursively call it on other vertices of the graph. The first thing it does is it visits the current vertex U, which means it does some computation on it. Right now we don't really care what that computation is. There could be 1,000 different things depending on your application. Once we've finished visiting the node and doing our computation on it, we mark its visited flag as true so that we don't ever accidentally visit that node again and do the same computation over again. And then we have a for loop that goes through all of the edges out of U. So we look at all of the edges going out of U. We look at the vertices that they connect U to, and we ask, are any of those not visited yet? So remember, exclamation mark means logical not. So if the vertex v has not been visited yet, then we will call depth first search recursively on vertex v. And that will look at its neighbors, and its neighbors will look at its neighbors, and so on. And that's the whole code. Again, remember we're assuming before we start that all visited flags were set to false. Before we did the top level call to DFS. And again, this method visit that we have up there might, for instance, add up the population of all of the different cities that we visit. So if you want to, for instance, add all of the population of all the East Bay cities, then you do a depth first search on that city adjacency graph, and each time you visit a city, you add Berkeley's population, Albany's population, etc., to the total. So let's look at how this pseudocode behaves on the city map that we had. No, sorry, the intersection map. Let's do the intersection map. So remember, it looks like this. And let's suppose that I start at node 1. So I do my very top level call to depth first search to node 1. So here's the program stack. So I call depth first search on node 1. And so I visit 1. I'll draw a little V here to tell us that node 1 has been visited. And then I look at all the edges going out of node 1, and there's only one edge coming out of node 1, so I'm going to follow it and check, has 4 been visited yet? 4 has not been visited, so I'm going to call depth first search recursively on 4, and then I'm going to visit 4, and then I'm going to look at all of the edges going out of 4, and there's only one. It goes to 5. So I call depth first search recursively on 5. I mark 5 as being visited. I look at all the edges going out of 5, and there's 2 of them. There's one that goes up to 2. There's one that comes over to 6. So I'm going to visit those in whatever order, if they're in the adjacency list in. So let's suppose 2 comes first. So I call depth first search recursively on 2. Now I look at all the edges out of 2. There's only one. It's the edge that goes from 2 to 1. Has 1 been visited yet? 1 has been visited yet, so I'm just not going to visit 1 again. So I don't call DFS 1. Instead, I look to see if there's any other edges coming out of 2. There are not, so we're done with node 2. And the recursion backtracks. We remove the top stack frame from the stack. And now we're back at node 5 again, looking for other edges out of 5. And there is one more, which goes to 6. So we do depth first search on 6. We look for nodes out of 6 after we visit it. We find an edge going to node 3, so we go to vertex 3. We visit that. We look for edges out of vertex 3. There are 2 of them. There's an edge going to vertex 2, but 2's already been visited. There's an edge going down to vertex 6. 6 has already been visited. So I'm done with vertex 3. So vertex 3 comes off the stack, and we backtrack. 6 has no more neighbors, so we backtrack. 5 has no more neighbors, so we backtrack. 4, 1. We backtrack to the beginning, and now we've visited every vertex once. Any questions about that? Mm-hmm. I think breadth first would have been slower and yet less and less malleable in the way you need to adapt it to Project 2. So I would not have chosen breadth first search for Project 2, no. All right, the last important thing to know is that this runs in big O of v plus e time on adjacency lists. But it runs what might be slower if you have a sparse graph in v squared time on adjacency matrices. Why does it run slower on adjacency matrices? Well, it has to do with this inner for loop right here. That for loop, if it's an adjacency matrix, you have to go through a whole row of the adjacency matrix and check every entry to see if it's true or false. And that takes order v time for each row. If you have an adjacency list, you only have to look at the edges. Your running time of the inner loop is proportional to the number of edges adjoining that vertex. And in all of the vertices together, you're going to be looking at each edge twice, so it runs in big O of edges time. Any questions about that? All right, on Monday we'll talk about breadth first search.